The last part of this section is to find the surface area of one of our parameterized surfaces. So let's say we're working with a parameterized surface. We're going from some region in the UV plane, which we'll call D, and that's being mapped through our vector valued function R to some surface in three-dimensional space. So we have some surface here. We'll go ahead and call that S. We're going to try to find the surface area of S using D. And that essentially is going to turn into some sort of integral over D, a double integral over D, that has something to do with R. But it's not just going to be a straight up integral of R. What we're going to do here is think about some little rectangle in D. So you have this rectangle here. Maybe I'll call that R. We're going to say one of the corners here is the point U0, V0. And let's say that the rectangle has side lengths of delta U and delta V. Of course, that rectangle is going to be mapped to something over here that's not necessarily a rectangle. So we'll say the point here is the image of U0, V0, and then the rest of it's just the image of R. We'll probably actually zoom in on that in a moment. Actually, maybe we'll do that right now. So we're going from our rectangle R with the point U0, V0. This is a delta U, this is a delta V. The sides are parallel to the axes. Over here, we have our image of U0, V0. We have some curves that are given by the actual grid lines here. These are actually grid curves. This would be the image of U0, V0. This would actually be the image of U0 plus delta U, V0, because this point here is U0 plus this delta U and the same V0 for the V value. And this over here would be R of U0, V0 plus delta V. How are we going to figure out what the area of this image is? Well, what we can do here is we can, actually let me do this in another color, maybe it'll stand out a little bit better. Let's think about connecting this base corner to these other corners. And, well, I'm essentially going to view these as two sides of a parallelogram. And if I complete that parallelogram, I might not actually end up meeting over there. So let's kind of maybe have it off a little bit. But as long as the rectangle R is kind of small, this parallelogram here will fairly closely approximate the area of the surface given by the mapping of the rectangle R. And so we can approximate the area as being approximately the area of the parallelogram. So we'll say the area that we're looking for is approximately the area of the parallelogram. Of course, that parallelogram has side lengths given in terms of vectors. So we're treating these points as vectors. So we can actually get the vector from here to here by actually subtracting these two vectors. We can get the vector from here to here by subtracting those two vectors. So we're really looking at R of U0 plus delta U, V0, minus R of U0, V0, and also the vector R of U0, V0 plus delta V, minus R of U0, V0. Now, if we took these vectors here and we divided them by the corresponding delta, so here for this one, if we divided this by delta U, this would be approximately equal to the derivative r sub u, because that's essentially what we're doing here. If we took the limit as delta u goes to 0, we would have the actual derivative at u naught v naught. Same kind of thing over here. If we divide this by delta v, this will be approximately equal to r sub v. That means that we can approximate the actual vectors along the sides of this parallelogram by the vectors delta u times ru and delta v times rv. And that's what we're going to do. We're going to approximate the area of the parallelogram by using these two vectors in our formula. Now, how do we find the area of a parallelogram? Well, we discussed this back in chapter 12. The area of a parallelogram is the magnitude of a cross product. Well, in this case, this is actually going to be an approximation because we're not actually using the two vectors that I have drawn here. I'm actually using tangent vectors, which are more like I told you to put that in blue. So this one here, this would be the tangent vector ru, and that one there would be the tangent vector rv. They're actually tangent to these grid curves. They're not the same as our actual vectors to these other points in our parallelogram, these other corners of our parallelogram, but the lengths of these are going to be very similar to the length of this vector once we multiply them by delta u and delta v. And while I've drawn these the angle here pretty far off, the smaller the rectangle is, the closer these will get. And so that's why our approximation will work here. So this approximation, I'll have a delta u r sub u and a delta v r sub v. Of course, delta u and delta v, those are just constants. They're numbers that we can pull out. So we can write this as the magnitude of ru cross rv times delta u and delta v. So once we've made this approximation, we're approximating the area of this piece of our surface by the area of the parallelogram, which is then being approximated by the parallelogram made up of these two vectors. If we break up the entire surface in that way, we can turn this essentially into a full grid of rectangles, and once we add them all up, we have a double sum of a bunch of r sub u cross r sub v's for various rectangles times delta u delta v's. Obviously, these values will be different for each rectangle, but I'm not going to get into all the notation here. I mean, technically, we'd have to label these by some indices of I and j or something like that. But we have a Riemann sum here, and as we take the limit, this turns into a double integral. So if we have a smooth parametric surface, remember smooth here means that our cross product is never going to equal 0. That's actually important because that's going to say that none of our rectangles end up mapping to some area in our surface that is 0, whereas it came from a rectangle that didn't have area of 0. Then, and S being covered just once, that has to do with things like if we use a parameterization of the sphere using sines and cosines, we don't want to have say phi go from 0 to 2 pi, because that would actually cover the sphere twice. Each point on the sphere would actually have two values of uv that would actually map to it, or phi and theta in that case. Then the surface area is just the double integral over the magnitude of ru cross rv over our domain D, where of course ru and rv are the vectors that we've been working with. Now, in some special cases, if we look at a parameterization like, if we're looking at, say, z equals f of x, y, remember we can parameterize that using our default parameterization. Here I'm not even going to relabel them. We're just going to say x equals x, y equals y, and z equals f of x, y. If you want to call them u and v, you can, but we don't really have to. In that case, keep in mind, r of xy is just xi plus yj plus f of xy times k. That means rx, if you differentiate everything with respect to x, derivative of xi turns into an I, derivative of yj is 0, and then we get the derivative of f with respect to x times k. I'm going to leave out the xy here. Same thing with y. The xi goes away, yj becomes a j, and we get the derivative of f with respect to y times k. If we take the cross product of these two things, so this is easy enough because we just have two terms each. I cross with j, that turns into a k. I cross with k, that's actually the wrong direction. It should be, if we follow our cycle, so that turns into a negative j. So we'll have a negative f sub yj. K cross with j, that's also the wrong direction. So we're going to end up with a negative I, or so negative f sub x times I. And then finally, the last pairing here, we have f sub x times k and f sub y times k. Well, k cross k is just 0. So our actual vector here is negative f sub xi minus f sub yj plus k. The magnitude of this is fairly easy. We just have the square root of f sub x squared plus f sub y squared plus 1. Or we can go ahead and write this as the square root of 1 plus the derivative of z with respect to x squared plus the derivative of z with respect to y squared. And we can go ahead and then put that into our formula. Keep in mind that we're going to be integrating this over some region D in the xy plane. And we get that the area of that surface is the double integral over that D of this expression. In fact, this is exactly the formula that we got back in section 15.5. We actually took functions of two variables and we were able to find the area of the surface above a region in the plane. In fact, all the stuff that we did with our parallelograms, we actually did very similar things back then as well to show that formula. But here, we're basically showing that our formula is consistent with what we already derived, which is always a good thing to know. As another example, let's take a surface of revolution. So we're going to take a function y equals f of x, some curve in the plane. The x is going to go from a to b. So we have some a, some b. When we take this and rotate it around the x-axis, get some surface of revolution. We can find the area on that by what we just did. Remember, our parameterization for this, we'd said x equal to x. You could give it a different letter if you want to, but I'm just going to keep it as x. Y is going to be f of x times cosine of an angle theta. Z is going to be f of x sine of that theta. Of course, here theta is going to go from 0 to 2 pi, because that's essentially saying we're going all the way around the x-axis. We can go ahead and differentiate, so keep in mind these are the components of r. R is going to be xi f of x cosine theta j plus f of x sine of theta k. If we differentiate that with respect to x, of course, the first component here just turns into an I. Then we have the derivatives of f, but the cosine and the sine don't change. If we differentiate with respect to theta instead, this time the x actually goes away. We don't have an I. This time the f of x stays the same, but now the cosine and the sine get differentiated. So cosine becomes negative sine, and sine becomes cosine. Now we need to take the cross product of these, and that's a little bit of work. I'll leave that mostly to you, but there will be some stuff with sines and cosines where you'll have sine squared plus cosine squared equals 1, stuff like that. But the end result gives f of x, f prime of x as your I component, a negative f of x cosine theta as your j component, and a negative f of x sine of theta as the k component. Which means when you take the magnitude of this, so notice here that everything is times f of x, and we're going to assume here that f of x is a positive value, so we can go ahead and pull it out. So we don't have to deal with any absolute values. If we had to take the magnitude where we allowed the function to actually go negative, we'd have to end up pulling out an absolute value of f of x instead of just f of x. But as long as we have a non-negative value for this curve, that's fine. That won't actually work for the sine of x that we looked at in the last video, but it would work at least on from 0 to pi, something like that. But we end up being able to pull out f of x, and then everything else, because the sines, we'll have a cosine squared plus a sine squared, which will turn into a 1, and then we have the f prime squared. Of course, since theta is going from 0 to pi, when we integrate this, we have from 0 to 2 pi, we have x going from a to b, we have all this stuff in here, dx d theta, but nothing on the inside here actually depends on theta anymore. So we're able to turn the integral from 0 to 2 pi d theta into just a 2 pi on the outside. We have a 2 pi times the integral from a to b of f of x times the square root of 1 plus f prime of x squared dx. And you might not remember this, but back in chapter 8, actually section 8.2, this was a formula that was actually derived for the surface area of a surface of revolution. It might not be as familiar to you as the actual volume of these things, where we use the disk method or the washer method, stuff like that. This was in that section, or in that part of Calc 2, but maybe not as memorable. But the point here is, once again, we have verified that a formula that we got, the very general formula that we got for areas of surfaces that are parameterized, does agree with all the formulas that we had from before. Let's go ahead and apply it to something that we haven't worked with before. So here we're going to find the area of a surface. They've actually given to us the vector equation r of uv equals u cosine vi plus u sine vj plus vk. This is what we call a helicoid. If we go ahead and graph this thing, so we have the surface, we have u cosine v, u sine v, where they told us that u is going to go from 0 to 1, v is going to go from 0 to pi, and we get this surface here. Now, it might be a little hard to tell exactly what's going on in this thing. Let's actually show it for a bigger range of values. So I'll go ahead and hide that, and we'll go back to what we had before. And instead of having u go from 0 to 1, let's have it go from -5 to 5. We are allowed to put in negative numbers here. And v, even though it is going into the sine and cosine, and you think 0 to pi would be fine, it is actually showing up outside of sines and cosines. That's our third component. So actually, I'm going to go ahead and take that from -2 pi to 2 pi. And so this is the actual surface that we have. This is what we call a helicoid. Technically, these actually do expand out to infinity. These are the only reason that we've stopped at here is because I've only gone out from -5 to 5. And then it continues going up and down as far as you want. That depends on the actual values of v. And in fact, the fact that we went from -2 pi to 2 pi is giving us 4 different levels of this surface. But once again, they're only wanting us to look at this section of the surface. So we have this kind of this little piece of it that's going about halfway around, or well, it is going halfway around, and only going out to a distance of 1. We get to go ahead and take derivatives. So we don't have to do any parameterization of this one. We just use what they gave us. So r sub u, obviously that becomes a cosine of vi plus sine of vj. The vk goes away. R sub v, this time we actually have to differentiate the trig part. So we have a negative u sine v times I plus u cosine v times j, and this time the k stays as a 1 times k. We do need to take the cross product of this, and this can be the kind of the time-consuming part of it. So remember, we're putting these as our bottom 2 rows. I'm going to go ahead and put the one that's going to be the longest down on the bottom, so RV is the longer one. So we have minus u sine v, we have a u cosine v, we have a 1. Then for the second row, we have a cosine v, a sine v, and a 0. And on top, we have the I, j, and k. The I here corresponds to this bottom 2 by 2. So we end up with the u cosine v 1. We have a sine v 0. That's our I component. We get to move on to j, which means we get rid of the middle 2. We have the negative u sine v. We have a cosine v here, and we have a 1 and a 0. But of course, remember the minus sign here. Though I guess the minus sign won't really matter when we take the magnitude later on, because we're going to square this eventually. For k, we have this 2 by 2 over here. We have a minus u sine v and a u cosine v. And on top, we have cosine v and a sine v. That's all times k. We go by diagonals, so we have sine v times 1 minus, well, 0 times something, so that part doesn't really matter. But we just end up with a sine of v times I. For this one, we have cosine of v times 1, and then again it's 0 the other way, so we end up with a minus cosine v times j. Then here, we have cosine times cosine, so we actually have a cosine squared times u, minus, we have sine times sine, so we have a sine squared. We're subtracting a negative sine squared, so we have a plus u times sine squared. In other words, we have cosine squared plus sine squared everything else has a u in it. So I'm going to just kind of cut to the chase and just make that into a u. There was a step I'm just not showing here where we just turned sine squared plus cosine squared into a 1. So actually, we got a very nice form for our well, this is, you could say this is a normal vector. This is actually a perpendicular to our surface at any given point. In fact, it might be a nice thing to take a look at that. Pick whatever point you want on our picture. I'm going to go ahead and pick the point. So u is going from 0 to 1, so I'm going to pick halfway between them. V is going from 0 to pi, so I'll pick halfway between those. And I'm basically plugging those values into A. They'll give me a point on my surface, which I'm going to make that a little bit bigger so we can see it better. Make it a solid black so we can see it. So we have a point A that's on our surface. If we go ahead and from that point A, we make a vector, and then we add on the RU cross RV. Remember, that was sine V, so we have a sine of, remember, that's pi over 2. Then we have cosine. Well, actually, we had negative cosine. Sorry, negative cosine pi over 2. Though actually, that will turn out to be 0, so the negative really won't matter. But then we also have u, which u was 1/2. That gives us a vector that is perpendicular to our surface at point A. So if you wanted to find the tangent plane there, you could use that vector. It's a normal vector, all that kind of fun stuff. It's not really what we're worried about right now, but it's nice that everything kind of is kind of bundled together that way. The result of all the work that we're doing to find the surface area is also the same work that we do to find the tangent planes. But to find the surface area, we're going to go ahead and take the magnitude of this. So that's the square root of, we have a sine squared of v. We have a plus cosine squared of v. We have plus a u squared. So we end up with a square root of 1 plus u squared. We're going to go ahead and integrate that. Keep in mind our limits on our u and v. So the area here, I guess you could say the area of the surface, is going to be the double integral. I'm going to put the limits on v here from 0 to pi. The limits on u are 0 to 1. We have the square root of 1 plus u squared du dv. Now, one nice thing that's happened here is that we don't have any v's left in our integrand. So I'm going to take the integral over dv of 0 to pi. That's just going to turn into a pi on the outside. So we're looking at the integral, or pi times the integral from 0 to 1 of square root of 1 plus u squared du. Unfortunately, this is a somewhat annoying integral. We could use a trig substitution here. I would use u equals tangent of theta or something like that. But we could also be kind of cheaty about it and just look up the formula in the back of the book. There's a reason why tables of integrals exist. In the back of the book, there's a table integral, and this is integral number 21. Specifically, there they have the square root of a squared plus u squared. So, but here a is going to equal to 1. The integral that we have there, this integrand, when we integrate it, becomes a u over 2 square root of a squared plus u squared, so 1 plus u squared, plus, I think it was an a over 2, but since a is 1, we did 1/2. We have the natural logarithm of u plus the square root of a squared plus u squared, so 1 plus u squared. Technically, we have a plus c on the end of this, but we don't need that when we're doing a definite integral. So maybe not the prettiest formula that you might want, but that's what we get. When you plug in 1, this turns into a 1/2 times the square root of 2 plus a 1/2 times ln of 1 plus the square root of 2 minus pi times, well, we're plugging 0 in there, so we get a 0, plus 1/2 ln of 0 plus square root of 0, not square root of 0, it's square root of 1. But here, what do we have? We have ln of 1, and ln of 1 is 0. So actually, this turns into 0 plus 1/2 of 0, or in other words, all of that is actually 0. So this is actually our answer. And I'll go ahead and pull the 1/2 out. We get pi over 2 times the square root of 2 plus the natural logarithm of 1 plus the square root of 2. And there's not really any nicer way of writing that. You can't pull the square root of 2 out of the natural log or anything like that. That's just what we have. That's the area of this thing. This piece of the helicoid. Maybe a little not as pretty as you might want it to be, but it is what it is. Let's do one more example. So here we're looking for the area of the sphere that is inside the cylinder x squared plus y squared equals a squared, where a is between 0 and b. Now if we go ahead and plot this thing, I'm actually going to plot it for a equal to 1 and b equal to 2. So here we have the sphere of radius 2, so that equals 4. And the cylinder, x squared plus y squared equals 1, because it has radius 1. And why did you make that a circle and not a cylinder? I'll be right back. Okay, now we have it as a cylinder, not as a circle. So we're trying to find the area of the part of the sphere that's inside the cylinder. So we're basically looking at the top here, and technically the bottom as well, though we could actually just find the area by just doubling one of them. So we'll take a look at the top part and not worry about both of them for now. There's a couple ways we could do this. One way, we could go ahead and just do it directly by solving for z. We could say that z is equal to the square root of b squared minus x squared minus y squared, and we can integrate over the disk of x squared plus y squared is less than or equal to a squared. In fact, this integral would not be too hard to set up, since we have a formula specifically for this kind of parameterization. This is our default parameterization, and we can use polar coordinates to actually do the integration over this disk. But instead, let's set it up using a different parameterization. This will make the integral a little bit harder to set up because we don't have the default parameterization already set up for us, but the integral will turn out to be a lot easier. So I'm going to use the parameterization based off of spherical coordinates because we are working with a sphere, so why not? That means that we are going to set x equal to our radius of b times sine of phi cosine of theta. Y is equal to b sine phi sine theta. And z is equal to b cosine phi. Of course, we are able to go all the way around. There's no limits on theta, so theta is going to go from 0 to 2 pi. But phi is actually going to be the trickier one. So remember, when we work with phi equals 0 is the positive z-axis. We're essentially going to go from the positive z-axis out until we hit where these intersect. We want to figure out exactly where these actually intersect. What value of phi are we going out to? And that actually kind of comes down to triangles. So if we think about it, let's actually maybe pick a point on that, on this particular, um, on the intersection here. So let's say, so remember the cylinder has a radius of 1. If we pick 1, 0, that is a point that is on the equation x squared plus y squared equals 1. That would be a point on the cylinder for any value of z. If I want to go up to till the point that x squared plus y squared plus z squared equals 4, so basically what would be the z value that would make 4 overall? So if I plug in 1 and 0 into my formula for the sphere, I get z squared equals 3. So I need to go up to a square root of 3. So actually, in fact, you can even say that the top is exactly where z is equal to square root of 3. But if we then make the line from the origin to A, I think it was A. Yeah, they called it A. And you can't really see that very well, can you? I want to make that thicker so we can see it better. So we have that line segment in the middle there. We can take the point on the z-axis of 0, 0, square root of 3. That's actually the center of this circle that we have up here. If we take the line segment from A to B, we have a triangle. And the important things about this triangle, so from A to B, remember that is a radius of 1. That's the radius of our cylinder. Or in the more general case, that would be a radius of A, because that's the radius of the cylinder. On the other hand, what is the hypotenuse? The hypotenuse, that is actually a radius of the sphere. In this case, that would be a radius of 2. In the general case, that's going to be a radius of B. So we have an opposite. So this angle here, which is our angle phi, that angle is part of a triangle with hypotenuse B and opposite A, and so we can find the sine of that pretty easily. So I'm just going to call this capital A. So that's an angle where the sine of that angle, remember sine is opposite over hypotenuse, and that we saw that was A over B. And since it's actually going to come up when we have sine of A equal to A over B, cosine of A, if we actually calculate what that is, so that would be the adjacent over the hypotenuse. So we're still going to have B on the bottom. We're going to have to figure out what the actual adjacent is. But we can use the Pythagorean theorem. That is going to be B squared minus A squared, or the square root of that. So we have the square root of B squared minus A squared over B. That's going to be relevant at the end. But for the moment, I don't really want to put inverse sine of little a over little b in all of my limits. I just want to put capital A there. It'll make it a little nicer looking. All right. Now we get to find r sub phi and r sub theta. So remember, these are the components of r. If we differentiate all these with respect to phi, sine of phi becomes a cosine of phi. So we have b cosine phi cosine theta times I plus b cosine phi sine theta times j. Well, this is now it's going to be a minus b sine phi times k. Differentiating with respect to theta instead. So the first one becomes a negative b sine phi sine theta times I. Then we have b sine phi cosine theta times j. And the z component goes away. We don't have a k part. we go ahead and take the cross product of these two. So we have r. Well, technically it doesn't really matter which order you do it in. I'm going to do r phi r theta. It's going to turn into a determinant. To save time, I went ahead and just copied them over. Remember, our top row is going to be ijk. And I forgot to erase this k. There we go. When we work this out, remember the I is with this 2 by 2. I'm just going to go ahead and find this 2 by 2 right now. Remember the determinant is, we go along the diagonal, so we have this times 0 minus this diagonal. So we have a b sine phi times a b sine phi cosine theta, but we're subtracting that one. So we have minus b squared sine squared phi times cosine theta as our I component. Our j component, now we're leaving out this middle part. We're dealing with these two and this one. Again, we're going to get 0 from that direction. Then we're going to end up with a 2 b's, 2 sine phis, a sine theta. We're subtracting it, so this minus sign goes away. But because it's the j component, we actually are subtracting the result of that. So we do get a negative overall. We get negative b squared sine squared phi times sine theta. That's j. Finally, for k, we're dealing with this 2 by 2 now. So this time we have b squared, we have a sine phi, a cosine phi, and a cosine squared of theta. We're subtracting, so actually adding. So b squared, sine phi, cosine phi, and a sine squared. So overall, we end up with a b squared, a sine phi, a cosine phi, and then we end up with a cosine squared plus sine squared, which is just a 1 that will go away. So that's our k component. The magnitude of this, which is what we're going to need to integrate, is actually going to simplify fairly nicely. In fact, this looks really complicated right now, but once we actually take the magnitude and simplify, things are actually going to turn out very nice. So we end up with, well, actually everything has a b squared. I'm going to go ahead and pull that out. We have b squared on the outside. Notice that it is actually b squared. It's not just a b, even though we took it out of the square root, because once we squared all of those, we had a b to the 4th power. In fact, we also can even pull out a sine of phi. Everything has a sine of phi in it. So I'm going to pull that out as well. Note here, sine of phi is a positive value because we are working with from 0 to a, where a is actually the inverse sine of something that's between 0 and 1. Keep in mind that that's why we had a between 0 and b. So I can go ahead and pull that out just as a sine of phi. So on the inside of our square root, we still have one sine of phi here, so we have a sine squared phi, and we have a cosine squared theta. Here we still have one of the sine phis as well, so we have a sine squared phi and a sine squared theta. Here we've taken out the b squared and the sine phi, so we just have a cosine squared phi. Here we have sine squared phi and a sine squared phi. We can factor that out. We have cosine squared theta, sine squared theta. That just turns into a 1. So we end up with just sine squared phi. But then we also have the cosine squared phi as well. And of course that turns into a 1 as well. So we have b squared sine phi. Now, actually this should not be surprising at all. Remember, b here is our radius. So you could actually view this as rho squared sine phi. It's exactly what we've been using when we do any integrals in spherical coordinates. In fact, this is exactly the computation that you do. Remember, you take the determinant of this of our Jacobian. And it essentially just turns right into that. The top row here is, I guess the top row here we have I, J, and K for now, but when we take in the Jacobian, they'd be the derivatives with respect to R to rho instead. But it turns out we get the same result overall. But the point here is that we're now going to take the double integral over that. Remember, theta is going from 0 to 2 pi. Phi is going from 0 to a, where a is our special angle that we haven't really messed with yet. We're integrating b squared sine phi. D phi, d theta. But there's no thetas in here. So actually the d theta, we end up getting a 2 pi on the outside. I guess we can even pull out the b squared from there. The integral of sine phi becomes a negative cosine phi from 0 to a. We go ahead and plug in those values. We have negative cosine of a minus a negative, so plus cosine of 0. We already found out what cosine of a is. That's why I brought this up earlier. I'm going to replace cosine of a with the square root of b squared minus a squared over b. And then cosine of 0 is 1. And just to make it look a little nicer, I'm going to swap the order of these, and I'm going to pull one of these b's inside. That will get rid of the fraction. So we'll have a 2 pi b times b, because I had to multiply it to both this and the 1 that's over here. We have b minus the square root of b squared minus a squared. Technically, that is the area of one of the caps. If you wanted to have both of the caps, you would double this. So 4 pi b times b minus square root of b squared minus a squared. But of course, that part's not that hard. The important part is how would you actually get the area of one of the caps. And this is one way we could actually do this. If you wanted to do it directly and actually just use z equals the square root of b squared minus x squared minus y squared and integrate using polar coordinates over this, you can go ahead and do that. The integral there is a little complicated. Not too bad. It's just comes down to a substitution, but you will get the exact same result. Okay, so I'm going to go ahead and leave this here. This is turned into the longest video of the 3, but this is the one where I actually had to do integration. In the next section, we are going to essentially take what we've done for surface area and actually use this to integrate other functions over a surface, rather than just finding the area of the surface. We'll integrate a function over that surface, and we'll get what we call a surface integral. So I'm going to leave this here, and we'll get to that in the next section. So see you there.